Hi, welcome to this video. We're going to talk about Commodore power supplies, the contemporary bricks of death that die, how they fail, why they fail, and how to make a modern replacement supply. Our new supply will be able to power several different models of Commodore 8-bit machines and possibly others too, whilst using the much more efficient switching type power supplies, and also taking a look at these switching supplies as they're not all born equal. Once we've assembled our Commodore supply, we're then going to take a look at a supply that's able to power the 1541 and 1581 disk drives. These have much more stringent noise considerations. So before we get down to the build, let's take a little bit of time to go through a small amount of the theory. Okay, so on the screen at the moment, we can see a basic symbol, a schematic symbol for a transformer. Now this particular transformer has only got one primary and one secondary, and we're going to label these up now. So what this means is that the primary is where the power comes in. The secondary is where it goes out. Now a transformer works by magnetic induction. It creates a magnetic circuit between the two coils. They don't actually touch, it's the magnetism that actually creates the current that goes across. Now this means that in order to induce a current, it has to be changing. So we're talking about AC here. It is possible to do it with DC, but that's well out of the scope of what I'm explaining here. So what we've got here is AC coming in. AC going out like that. Now the ratio of the difference in the number of windings between the primary and secondary determines whether the voltage changes upwards or downwards on its way out. Now transformers are given a rating and it's called VA, and that stands for volt amperes, and that's basically almost a direct equivalent for watts. Now I need to say at this point that before any electrical engineers start jumping up and down and start going mental, I'm really going to take some serious liberties with how I'm going to explain this, just for the simplicity of it. So what we're going to say is this is an ideal transformer. Ideal means that there's no losses involved, and that keeps everything nice and simple. Now later on in the build we're going to be using a 30 VA transformer. So let's put this in the top here. Now 30 VA means that 30 equals the volts times amps. Now because you get the same power coming out as you put in, you can then work out how much current you're going to pull. So as this is 30 VA, we know our input power, if you're living in the UK like me, is going to be 230 volts, but it's going to be 30 divided by that, and that will give us our amps, and that will equal 0.130 amps, or 130 milliamps. So on the live main side of it, it's going to pull bugger all. No problem. On the output though, we're going to have 30, and that's going to be divided by 9 volts. And this is what our SID chips use. In the Commodore machines, it's basically the SID chips that are going to use the power. The CIA uses it for TOD, but that's the time of day clock. That's a little bit of a different matter. It just uses it as a time base rather than a current source. So 30 divided by 9 volts, this gives us, oh look at this, 3.33 amps on the output. Now this is enough to power an old 2-prong VIC-20 as well, in case you want to do that. So what we're saying is that our 230 volts is getting transformed down to 9 volts on the way out, but the amps is going up in relation, so it's still 30 times volt amps on both sides. Now as I've explained it here, this is a really simple transformer, and you can actually use this, you know, to power your Commodore, no problem. Here we are with what looks like two transformers next to each other. It actually is not. It just means that we've got two primaries and two secondaries on the same transformer. Now, as we're creating a magnetic link and nothing's touching, we can wire these in different ways. This is exactly the type of transformer I'm going to be using in the build. I'm now going to explain why it's got two primaries and two secondaries. So up the top here, we're just going to put, it's still 30 VA. Well, secondary 1 here is 9 volts. Our secondary 2 here is also 9 volts. Our primary 1, well, that's going to be, let's say it's 110 volts. Primary 2 is also going to be 110 volts. So again, everything's AC. No DCs or transformers unless you want to blow the arsehole out of something. Okay, so there we go. AC coming in, AC coming out. So coming in, we've got two choices. If we was to live in America, we could have 110 volts coming in, and we would simply link, that is shockingly bad line that. We're going to link that one together. And then we'd link this one and this one. We're going to go over that with shockingly bad drawing there. So if we lived in America, we would quite literally link them together like that. Now that's a parallel connection. The top of this coil here is joined to the top of this coil here, and that's really important. And that's also why you have these circles here, as to say which way round that the AC is. Because if you turn AC the other way round, it literally does it the other way round. Let me just highlight that over here. So if we say this is our super wonky AC signal there, and we've got our probe on the top and the bottom, if we reverse our probes, it then looks like this. And when you add those two signals together, you actually get 0 because they counter each other out. That's a really interesting concept, and one that you've got to keep hold of if you're wiring primaries or secondaries in parallel. So let's just get rid of that now. Okay, so here we are. In parallel, we've got 110 volts for the secondary, primary. The secondaries, you've got two 9 volts there. Now that means you can create two circuits, but the VA will always add up to the same. So if you was to create two separate 9 volt secondaries, they would each have half the VA value, which would be 1.67 amps. Now let's go back to what we're going to do in the UK, where I clearly am. And all we're going to do is we're going to link here and here, and then we're going to come in here and here, and across these 2 points, right down there, that's going to be 230 volts. Lovely jubbly. That still gives us the same VA value. If you're going in with 110, quite obviously your amps are going to change on your input side. But for 230, they're going to be 0.13 amps. I think for 110 it'll be probably 0.26 or a little bit higher. As we're not talking about 220 volts, we're talking about 230. Now on the output side, for the purposes of what we're going to do with this build, we're going to parallel these up. So we're going to literally take this one here to output, we're going to take the same phase side, which is the one closest to the dot, to the output, and then we're going to join these two up like so, and we're going to come out here. Christ, that's wobbly. Right, there we go. So here we've got our two output lines, and this is going to give us 3.33 amps on the output. So going back to the last video, even though we've got twice as many coils in our transformer, we're going to configure it so that it takes 230 on the input and only 9 volts on the output. Okay, so on the screen at the moment, we've now got a simplified schematic of the Commodore 64 brick of death. So we can see here that we're coming in at 220 volts. It's fused, and on the other side of the magnetic circuit, you've got two 9-volt secondaries. One of them is going out as 9-volt AC, and that will go into power your SID and your TOD on the CIA chip. Your second one is over here, and it's going to get rectified. Now, rectified is where you turn AC into DC, and that's going to be quite an important concept for what we're going to say in a minute. So let's just explain that one. So as it goes through each one of these diodes, the power can only flow one way. Now over here, if we draw a really dodgy AC wave like that, we can see that some of it is above zero and some of it is below. So you've got some negative voltage going on there. Well, what the rectifier does is it essentially does this, and it flips the negative side above, and it does that by its root going through. Because you've got 4 in a link like this, when it's positive, it'll be going in this side and then returning up here like that. So it'll be going this way, and this side will be positive. Yeah? Now, take a step back. When it's negative, however, just like swapping your probes over earlier, this side will be flowing through and it will be coming back through here. But that also means this is positive. And this line stays negative. So your bridge rectifier, which is what this 4-diode arrangement is called, as a diode bridge, essentially turns the negative half of the wave positive. So we've got our DC, and then it's going to go up like that. But as you can see, that looks pretty damn rippled. There's bumps in it all over the place. And that's why we have this bad boy here. This smooths it out, and it's a capacitor. So basically it stores energy, and as the input starts to fall off, it takes it from the capacitor. So then your input looks something like this. If this is a DC wave, it will look like this, because the capacitor has smoothed it a bit. Nothing too serious, but it does help smooth it out. Now, here we've got a voltage regulator, and this is really the main crux of the problem where the brick of death fries your Commodore. You see, when you come out of this 9-volt supply here, you're at 9-volt AC. It says 10 volts here, but it's going to be a little bit different than that. You see, the 9-volt AC coming out is in RMS. And that means that in order to convert it back to DC, there's a little bit of maths involved. But basically, we're going to go up by root 2, which is 1.414 volts, and that will give us 11.36 on the back end after we drop our volts, because we've gone through two diodes. So what we've got is 9 volts times 1.414, which gives us 12.76 volts. So over here we've got 9 times 1.414 equals 12 volts, 0.726. Okay, but each time we go through a diode we have a voltage drop because it's a semiconductor, and that's usually around 0.7 volts. I know I'm going to have people jumping up and down, but anyway, for simplicity's sake, we're going to drop 1.4 volts. So out of that 12.726 minus 1.4, we're going to end up at 11.3 volts without a load. And that's coming out of here. It's going to get averaged down through the capacitor and things are going to get a bit funky, but all we need to know is it's going to be higher than what's coming out on the back end. Now this is another massive abuse of electrical engineering, but here we go. Just for simplicity's sake, the voltage regulator needs 2 more volts going in than what comes out in order to operate. Otherwise it's in what's called a dropout mode, and you lose your arsehole on the back out. You know, your voltage coming out starts to have voltage drops in it, and it's really quite funky. So you've got to be at least 2 volts above it. So over here we can see 5.2 volts is supposed to be going into your Commodore. Okay, so we need a minimum of 7.2 volts going in at the front end. So here we go, we're going to go back to our rubbish sketch like this. So what we're saying is at the bottom of this dip here, that needs to be a minimum of 7.2 volts no matter what current we're pulling, otherwise you're going to get dropouts going into your Commodore. Now this is the schematic for the brick of death, and the really simplified abridged version as why this blows the arsehole out of your Commodores is that this bad boy here, the voltage regulator, when it dies it fails typically as a short. So whatever voltage we've got here ends up going straight to here. Now the MOS chips in the Commodore, they can take, I haven't got a data sheet to hand, but I think it's around 7 volts to the def. But as you can see, it's going to go plus 10 at least, and it will blow the entire arsehole out of whatever is connected in the Commodore. This is typically why the brick of death is called that. They fail at the transformer tends to be okay. The voltage regulator loses its shit and just passes current straight through. The Commodore can't take it, and some of the poor logic chips end up dying. The second thing about these power supplies is they're linear in nature, and that means that you've got a transformer, it goes through some passives, through a voltage regulator, which is really just an arrangement of transistors and stuff, and it comes into the Commodore. As we know, the voltage on this side is higher, and that means that if we're pulling 5.2 volts here on the back end, we've got 5.2 times whatever the current is. So if that's 1 amp, we're pulling 5.2 watts on the back end going into the Commodore. Yeah, no problem. That also means that whatever the voltage is here, you also are taking 1 amp through it. Now, you don't need to be a genius to realise that this side is going to be massively higher than the output side. So where's all that extra wattage going? Well, it gets turned directly to heat. That is completely direct heat conversion. And that it means that the 7805 chip there is going to be frying its tits off. Now if you look at the data sheet, I think from memory the 7805, that can run at up to 150 degrees C before it loses its shit. In this case, you're literally going to be dumping 5 watts. And if it's 20 degrees Celsius per watt, that's going to be 100 degrees that you're going to be just dissipating as heat. Add to your ambient temperature, you could be at 120 degrees. It's obviously not enough to be melting it inside its potted compound, but this is the reason why linear supplies get hot. They're not very efficient and it's a direct heat conversion. They all work in a similar way. If you've got a voltage regulator, you need to keep your input as close to your output as possible without dropping out, purely for that reason. So let's just go back a bit. So what can we do about these bricks of death? Well, apart from replacing them, some people out there have made what they call C64 savers, which you may or may not have come across. And that basically looks at the voltage coming out, and as soon as it gets a bit squiffy, it clamps it down. So it tries to protect your C64. Some people have put a Zener diode in the C64 across the 5 volt and ground line to act like a sledgehammer. So as soon as it goes past 5.4 volts or whatever the Zener is, it just, boom, conducts straight to ground. These things are now coming up to 40 years old. If you use them, at some point they're going to fail. If they fail, they will kill your Commodore. No ifs, no buts, boom, you've blown your arsehole out of it. What you can do is take them apart and replace the voltage regulator if you can get to it, because a lot of them are potted to death. You can have a look at the capacitors inside and change them, but really you want to hide into nothing. At some point it's going to kill your Commodore. Now let's leave this there out and go on to a switch mode power supply. Okay, so for the build we're going to be doing, we're going to be using a Meanwell power supply. Now, according to the Meanwell datasheet, on the screen at the moment is a block diagram of how it works. And we can see that we start off with an EMI filter here, which basically takes out the electromagnetic interference from your source input, which is your main supply. It then gets rectified and filtered down, and that means it's turned into DC. This is where the magic happens, the power switching. And what that does is, rather than dissipate the extra energy as heat, it really just turns it off. So, to illustrate, if I just do another crap drawing, what it does is it creates a square wave like that at a certain distance here. Now as it's turning on and off, you get a ratio. So let's say that this here signified 20 volts, yeah? But it's only on for 50% of the time. Then clearly the output would equal 10 volts worth. If that makes sense. So it can regulate your supply just by turning it on and off. Now the actual control is called PWM, which is pulse width modulation. That's a little more complicated. There's different ways of modulating it, and it allows the small microprocessor on board to effectively track the changes in the load and keep the voltage stable. And that's why we've got a detection circuit on the back end here. This part here, as it draws all over the rest. You've got OVP, which is over voltage protection. You've got current protection. So the switch mode power supply itself, although being far more complicated, all it does is it switches the power on and off very, very quickly. And I'm talking about in the kilohertz range. So when it comes out, you get a very stable power supply. And nothing's really wasted power. Well, some is. Some of it goes out as heat. You're always going to have switching losses. But for the purposes of what we're talking about here, it's super efficient compared to a linear regulator, which, well, that's just bollocks, isn't it, really? So the switch mode power supply is usually in the 90% sort of range, according to what you're pulling and the application. These are massive oversimplifications now. So as it comes out, the only real problem is noise. And there is an absolute metric shit ton of it. Because you're turning it on and off so fast, you're going to get noise. Now in the data sheets, that's usually given as a figure point or peak to peak. Now as we're going to find out later on, I'm going to load up a cheap power supply and it looks like the Himalayas. It's just shit everywhere. And this is why you've got to be a bit careful when you spec a power supply to build. If you get a £3 AliExpress one, trust me, I'm going to show you one later, it's diabolical. When you're powering something other than a Commodore 64 or 128, you may not have the luxury of huge reservoir capacitors inside the machine. Now this is something that we're going to touch on with a 1581 because there's bugger all capacitors in it. So it really needs a regulated, smooth power supply. Otherwise, things are going to start getting a bit twitchy, especially where the disk drive's concerned. You're going to start getting weird spurious errors with reading and writing, especially writing, because as the voltage is going all over the place, so is the supply in the drive. So according to, going back to this power supply here, these work in a very similar sort of way. The input is smoothed out. Anything too dodgy is filtered out, and then it gets turned into DC. The DC employs several different modes in which it tracks the load and regulates it by switching it on and off. And this can be through an IGBT or power MOSFET or whatever. Then in this particular one, you've got another transformer. You've got a detection circuit for what is actually being outputted. So in order that it doesn't get away from itself, it always works in a closed loop. So it samples its own output and then it creates an error value and then modulates that in order to bring the error to zero. The controls inside, it's usually done on a chip. They've got switch mode power supply chips that takes care of all of that kind of thing. But being such a complicated piece of equipment, you get short circuit protection, you get over voltage protection, all are standard with switch mode power supply. So the chances of it passing anything nasty through are really lowered by a large amount, except this bloody switching noise. Now we're going to fire up the scope later on in the video, and we're going to load up a power supply, and we're really going to wring the arsehole out of it, and we can see exactly what it does then. But basically what you end up seeing is once you switch it into AC mode, your scope I mean, you're going to get this, and it's like a baseline noise going across it, and that's going to be present all the time. And the figure it gives you, well, some supplies are not equal to others, and some of it is truly diabolical. I mean, a good part of a volt different. And that's not really what you want, because logic chips are happy between, let's say, 5 and 5.3 volts. Sometimes they go down to 4.75 and 5.3 at the outside. So it's only really just over half a volt difference on its supply line. And some of this noise can seriously interfere with that. I know it's transitory and it doesn't last very long, but it can still cause problems, especially with 1581 drives. They're really sensitive to it because there's no extra smoothing. So let's clear that out. Now, for the purposes of our first build, which will be the C64 C128 power supply, I've gone with an absolute monster. It's a 10 amp Meanwell supply, and the reason for it was cheap. It was like £5 off eBay, brand new, delivered. Yeah, I'm not going to need 10 amps. 10 amps will light up bloody several C64s. But if you've got a couple of SID chips going, you've got stuff hanging off the back end, you know, like some serious cartridges, you can start to pull a bit more, especially if your cartridges have got like a pi in them. You know, you're talking 300 milliamps plus there. And if you've got, you know, a Pi 1541 and you're powering that from your C64 as well, you know, you're starting to pull a bit more then. So it's always worth having the headroom, because it'll run cooler and it won't redline what you're trying to do. So if you're running just a stock C64, you're not going to need more than amp and a half on your 5 volt line. If you start hanging stuff off of it, then yeah, you're going to want a bit more juice, otherwise something's going to give. Luckily, like I said, with switch mode power supplies, they tend to shut down rather than just, you know, burn anything out. It gets to a point they just turn off, so it's not too bad. They don't generally fail badly. I'm using 2 at the moment that I made 7 years ago, and they're absolutely cheap, chinky jobs, and they've been brilliant. But they've only been used on a C64 and C128, and they've both got massive reservoir caps, which make it much more forgiving. Okay, so here we've got a basic overview of how a switch mode works. I know I've completely bastardised the electrical engineering side, but hey, shit happens. The next thing we're going to look at is we're going to fire one of these up and see what's going on, especially noise wise. Okay, so here in front of me I've got an electronic load, just a cheap one from AliExpress. They're about 15 quid or so. I've got the 10 amp power supply that we're going to be using for this build, and we've got a scope that will come through on a different screen. Over here I've just got an IEC connector. We're also going to be using this on the build. These come from AliExpress. They're really quite cheap. They're only about £1 something, but the good thing about them is they come with leads already pre-made, so that's not too bad. So regular kettle lead, Meanwell RS50-5 supply, 10 amps, 50 watts. Okay, now the first thing we're going to do is give this some load and see how the waveform changes. So let's turn this on, hopefully not blow the arsehole out of anything. Okay, right, so right now we're at 5.14 volts at 1/4 of an amp. The scope is around 100 millivolts ish. I'll bring up the scope display as we go. Right, so let's give this power supply beasting. So when we take this down, we'll see here 5.15 at 0 volts. Sorry, 5.15 volts at 0 amps. Get that right. So let's start turning up the load. So we're just over an amp now, and the voltage has dropped to 5.09 amps. Volts, even. Bloody hell. The main thing to realise here is the more load that we pull, the more the voltage is going to drop. Now switches are quite good at regulating it, but they're still it's still going to drop, and that's just how it is. People have said on Facebook, oh, why are you using 10 amps, you'll never need it. Well, check this shit out. So let's crank this bad boy up, and we're going to go into 2 amps just over, and we're now down to 5 volts. So we started off at 5.15 volts, which is fine, that's no problem. The chips will be happy with that. I mean, realistically we could tweak that to 5.25 volts, but what happens when we start pulling more current? At 3 amps we're down to 4.95 volts. Now, as I said earlier on, the voltage tends to be okay as long as it doesn't drop between below 4.75. That is an absolute hard floor. Realistically, you want to keep it as close to 5 as you're going to get. Now, at 3 amps, that's not bad. So we've got a 10 amp supply, and we can regulate nicely as long as we only pull 3 amps from it. Let's give it some more grief. 4 amps, and we're at 4.90 volts. Holy shit, that's dropping there. Let's give it some more. Once we pass 6 amps, we're at 4.76 volts. This is going to be the absolute lower floor that we want to be pissing around with, especially with the Commodore. The scope's output's changed. We're getting a lot more ripple noise at this load, definitely. So, to begin with, whilst we're pulling 1 amp, we're getting around 100 millivolts of ripple, which is not bad at all. It's starting to creep up a bit more now. It's at 200, but we're pulling 6 amps out of it. So again, yeah, it's not too bad. Let's just see what happens when we really wring the arsehole out of it. Okay, so yeah, we're getting major fluctuations now. I'm measuring at 20 megahertz bandwidth, and it's, yeah, we're getting quite a bit of noise there. Let's drop that back down. A lot of the stuff you see on the scope, it's also picking up just ambient noise as well, and that's going to happen. See, if I turn off the power supply, this is what you'll get just on the Pro pickup. Once it dissipates, done. See, you've got a fair bit of noise going on there anyway. It's just different harmonic. So, for this first attempt, the meanwhile supply, it's not, yeah, it's barely lukewarm. We'll only run it for a few minutes. It doesn't look too bad, so I'm gonna just hook up another one now. Okay, so here we are back again. This time I've disconnected the meanwhile, and I've hooked up a 5 amp 5 volt 4 amp cheap Chinese supply, a similar type that I used on my last build, which was years ago, like 7 or 8 years ago, something like that, and it's been working fine. So literally China, eBay, as cheap as chips. So let's see how this one performs. So straight off the bat, with no load, it's regulating at 5.10 volts. These can be altered with the small trimmer pot on the front. Let's give it a little bit of current now. Right, so now we're pulling just over half an amp and well, that's not that bad. It's certainly not massively worse than the mean well. Now just over 1.25, well, just about 1.25 amps. Let's see. Kind of hard to adjust these loads. Right, we're down to 5.04 volts, and we're starting to get a little bit more noise there, but still, again, nothing more than the mean well. Let's creep this up to 2 amps. That'll have to do. So at around 2 amps, we're pulling 5 volts at 2 amps, roughly. And, well, yeah, there's a bit more noise. Is it any more than the mean well? I don't think so. Let's crank this up at 3 amps, or 3.14 amps. The noise has really started to rack up now. So let's just dial that back a bit and see what the cutoff point is. Because I think, yeah, anything over 2 amps and it really starts to go a bit mad. Let's right, we're at 3.93 amps, so we're close to full amount now, and it's absolutely doing its tits on the scope. So the noise is really ramped up, and although the mean well did the same thing, what we can take away from this is clearly that if you're only using half the capacity of the switch mode power supply, you're going to get much better noise. Let's take this back down. Okay, so we're going to do one more test, and I'm just going to set up for that. I'll be back soon. Okay, so here we go again. Now, this particular beast I've got here is an AliExpress special. It's a disk drive power supply that I cut the end off and put a 4-pin DIN connector for a 1581. However, I mean, this thing was £3 delivered, so my hopes were not very high. In order to use this, it's got 5 and 12 volts in one unit, so it sounded like it fits the bill. Unfortunately, I don't think it does. So if I just give this some power, and I've had to hook up some LEDs to the 12 volt line just to make sure it's loaded. Some switch mode power supplies that are dual, they key off one of the two lines. So if you've got a 5 and a 12 volts, maybe the 12 is the master, and that's what it uses for regulation. So here we go, we're at 5.14 volts, 0.34 amps. Yeah, it doesn't look all that great. Let's spin this up. Oh my god. Right, at 1 amp, we've already dropped to 5 volts, and the noise, holy shit, that's through the roof. This is absolute fucking garbage. There's a reason why it's £3. You can't use this on a 1581, it's just noisy as shit. You've got no filtering on the 1581 side, so what you're left with is just a pure input from this piece of shit. And I've got spikes up to 400 millivolts, and that's coming up to half a volt. That's just absolute diabolical, and I'm only at 1 amp. And this is rated for 2.5. So I know that the 1581 only pulls 1 amp, but do you really want to risk it? Because it's already done its tits already. If we go down to half an amp, it's back up to 5.10 volts, and it looks a bit more okay, but can you guarantee it's going to stay at that? No, not really. Not really. We go past sort of 1.5 amps, or up to 1.5 amps. Let's have a look. Let's see, I'll tweak that there. Yeah, we're down to 4.85. Fucking hell, look at the scope. It's like the fucking Himalayas. So the short of it is, it might be okay to test something, but I really, I'm just not going to use it. What a fucking piece of shit. Stay away from this garbage. Now I've got courtesy of 8-bit Retro ReFix, check them out, a 1581 board. So if I power this down a second, there we go. Turn that off as well. Good. So here we have a 1581 board. We can see that we've got absolutely no filtering on the input side at all. It's just, there's nothing. So it's expecting a nice, clean, regulated supply. Now on the other hand, a C64 or C128, well, they're happy as Larry with a little bit of little bit of noise, because they've got massive great capacitors on the main power coming in, which I think I might have one open here. It's the junker. Right, this was like £6 or something, and I repaired it, and I use it just for testing stuff out really. If I make a cartridge up or something like that, then this is the test machine. I mean, look at them, what an animal. There we go. Move that out of the way, we don't need that now. And I'll just shift that over a bit. Okay. So, inside here, look at that. Straight coming from the power in. So, you know, you've got a fair bit of smoothing on its way into the machine. So, it's not really a problem for these machines. However, it is better to have a lower amount of noise and ripple, and I know I'm going to get flamed for calling these two things the same thing. Noise and ripple are very different things, but I'm going to lump them together for the purposes of what I'm explaining here. It's better to have less noise and a more stable supply, especially if you're going to be pulling a lot of stuff through your C64, C128, or if you're going to hook it up to something else. Like I said, the build we're going to do shortly is going to be able to power other machines as well. So it's going to be semi-modular. You'll be able to change the lead and just hook up different machines. The 2-prong VIC-20 being a good one, because that requires quite a juicy 9-volt AC supply, and what we're going to do is going to have that. Alright, warning. We've got mains voltage here, so if you end up blowing your arsehole out, the cat, the dog, your missus, your house, or God forbid your Commodore, that shit's on you. Okay? Cool. Okay, here we are. So, I 3D printed a case, as we can see here. I know it looks maybe a little bit big, but I'd rather have it with some adequate airflow than something I'm struggling to get it all wired up in. So, in the design here, I just have some pieces, as you can see, end pieces that fit in the front, grills for the back, and I'm a big fan of only having the 4 screws in it, so the top and bottom hold it together. Now I've printed this in PETG. It didn't use a lot of filament. I'd estimate that the whole case probably costs around £4 to build. Now for this one, this is the C64 one we'll go with first. We've got a 10 amp supply here, and I've made it so that the power supply is captive in these blocks. There's a small gap underneath here for the airflow, although to be honest with you it's a solid bottom anyway, so that's not really going to matter a shit, is it? In the top, this spigot here will actually hold the power supply down, so, and these two cutouts here lock into these corner bits here. So if I just fit that like so, we can see exactly how it holds it in there. So that power supply is absolutely going nowhere once we screw the case together. Now, I've put this strange raised star arrangement on here because this spigot is going to provide a secondary mounting place for the toroidal transformer that I'm going to use. And that's going to just slip over that, and with the help of this funky spider here, it will literally sit like that, and this will give it some airflow between this and the case. So let's start with the components here. We've got our regular IEC. As you can see, I cut out a 3D end plate, so that will just go through there. 2 countersunk M3 screws, done up, lovely jubbly. These things are excellent. They've got a fuse and they've got a switch, so that saves us some time. Another cheap Chinese fuse holder, that just goes through there. So what will end up happening is it just unscrews like so. Now there's 2 plastic washers here. I don't really think they're going to be necessary when we're mounting it up against the plastic anyway, so it's got a shoulder on it, so that will just go through to the shoulder like so. We'll drop the washer on the back like that. We could use both of them, it isn't going to matter a fuck. And then we'll tighten that bad boy up, slip it over the solder tag like so, and then that will just sit there like so, like that. There we go. Let's get the IEC out for a moment, it's easier to see then. Then our fuse holder will just screw in the front. Now we're going to make this modular by using something I used a long time ago on my previous power supplies, and they're these type of aviation style connectors. And before the end of the build I'll pull out my old power supply and we can have a look. But these are nice and easy to use. As he says, as he drops one. So what we do is take that out, and there's 2 flats on it, so we just locate that and pop, and it goes, and then that does up. And I mean, obviously when we come to wire it, we're going to tighten it all up properly. Once we fix the wires to the back of this, I'll use a dropper heat shrink once they're soldered on. The other side of the aviation connector looks like this, and that just pushes in, and then it's retained by this thumb lock just on a screw thread, so it won't come out on its own. It comes out quite difficult. There you go. These are quite good. They can take several amps of power. I think this particular one takes maybe 6, I should think. But we're not even going to be pulling anything near that, so I'm really not concerned. And then we've got the ubiquitous displays that everyone uses. They're very cheap. They're easy enough to use. So all we do is you pop out the sides it will come out. He says. A small screwdriver. Come on. There we go. So you pop them out and there we go. You just take this. We're going to push that through the orifice in the front and we're going to drop that as well. So that will just pop out like that. Now it's important to take this out first. I'll retrieve that plate in a little while. It's important to pop that out first because once you put this back in, it will literally push the sides out like that and provide force so that it won't slip out. As you can see, it doesn't look too bad like that. Let's just pick that up. So let me just drop that back in there like so, and I believe that goes in that way. Either way, I'll check. I've got a few more of these, so I'll check which way around before I put it back in. And then our front panel will look like that, or rather like that. So it looks quite neat, tidy. Although you've got the IEC cable going in the front, I like that idea because you can turn it on and off from the front and you don't need any extra parts and what's really necessary. There's plenty of airflow in here and plenty of room once we get it together, as we can see there, to get all our wiring done in here. So that's why I like to make it a little bit bigger. Let's just half assemble this a second so I can move it out of the way. Just drop all that together. And then we're going to talk about what we're actually going to do. There we go, just pull that to one side. So what we're going to say is, we've got our IEC here and our 5 volt PSU here. And we're going to have our extremely shit transformer drawing here. So this is going to be our 30 VA 9 volt transformer. We're going to come in with live for a fuse. Let's just signify the switch there. So we're going to come in from the main side into a fuse. Call this mains. It's going to go through the fuse, through the switch, same as the neutral goes through the switch, and into our 5 volt PSU. Earth will go straight through, no problem. So it'll be live, neutral, earth. Yeah. Now 2 of these wires are going to be split off and I think we'll join them at the power supply when I come to build it. So as I said to you in the earlier part of the video, we're going to jump over the input side and this gives ourselves 230 volts. So this one's going to come up, go to the live. This one's going to come up, go to the neutral, don't need an earth on it. And that's how that one's going to sit. Now, we're missing something actually. On the live side, there's going to be a fuse, secondary fuse. That's what's going to be in the front of the panel. So, as I showed you earlier, on the output side, what we're going to have is a paralleled up output. So, what we're going to say is if this is our plug, and these are our 2 9 volt AC outputs, we're going to join these two together, and then they will come down and go into that one, come down and go into that one. Superb. And these two are going to be our 5 volts. This is where it's going to get a bit funky now. as this is the third time I've drew this schematic and fucked the last two up. So this is our display, and what we're saying is that our positive on the power gets split. So our 5-volt outputs here are going to come straight out, go to the power supply. Yeah, this is plus 5 volts DC. Yeah, you think that's a bit fucking weird. 2 wires are going to come out of this and join them here. So it's going to get split into 3 wires. We've got red, yellow, and this one's going to go to there as well. So basically 1 wire out of the PSU goes to 5 volts on the positive side, and it splits into 3, red, yellow, and then our supply to the plug. Okay? It's a bit fucking strange, isn't it? I agree, it is. But that's because if you're measuring your voltage, it's in parallel, and if you're measuring current, it's in series. So what we're going to say is that for the negative, we're going to come out, come around here, go into it there, into the display, and we're going to come in on the black wire. We're going to come out on the red wire, and that is going to go out to our 0 volts. So whatever current we're using is going to flow through the entire circuit. Oh, look at that, put a fucking wire on there, that's better. So look at that, what a fucking mess. But that's essentially what we've got. So it's not too complicated. We're fusing the primary side of our transformer, and that's because the secondary side is only going to pull what it's pulling. Even if this goes to short, it'll try to pull more this side and it's going to blow this fuse. So we're going to say that that fuse is our protection. So the fuse in the IEC block is going to protect everything. The current is going to return through the circuit and go back through the display our amps. And our voltage sensing is going to be from the black wire to the red and yellow as we join them together. So when you have a look at the small module, on the back of the unit you'll see there's 2 plugs. So this larger one is our current, and that's what we're going to wire into here. And I've written the colours on there because they come pre-colour coded, and that's what we've got. So for the current, as you can see here, it's red and black, these 2. And on the 3-pin connector, it's going to be red and yellow joined together, and the black can go fuck itself. It's not needed. Not for this configuration anyway. And that's it. That is completely the entire build. So what I'm going to say is, I'll get the components lashed together, and we'll go from there. See you in a minute. So this is a power supply that I built a few years back, and this is before I had a 3D printer. So I bought just a box, project box off eBay. I think it was like about 14 quid, an ABS plastic project box. Obviously that's what I've modelled the other one on size wise as well. We can see that I've got the same connectors from before. In fact, I had the ones I'm going to use in this build left over, even though it's so long ago. So let's have a look inside. Apologies for the mega lash up you're going to see now. And take these apart. And these have been running well for, like I said, over 7 years. Even want to come out of that one. So here we go. I have to stop saying fucking so. This is what I did before. Look at that tasty bit of chocolate blocking. Straight for the fuse, toroidal transformer, cheap as chips, chinky power supply, exactly like the build we're going to do in a minute. And yeah, I've used chocolate block, and yeah, it's been fine for all them years. You can see I've heat shrunk after I've soldered to the plug. That's always a good idea. That means that if anything does come off, it's not going to blow the arsehole out of anything by shorting it. And that's all there is to it. So this is the old one. Now this particular one, as you can see on the front here, 5 volts 6 amps, 9 volts 3.2 amps. So yeah, it's about the same rating transformer. I've got modular plugs, and what happened with this one is, this is my 128 plug. I got this off an Amiga. Someone had absolutely cooked the tits out of the power supply, so they were going to bin it, so I just cut the lead off, and there you go. I've also got another one that connects to a C64 or a cost reduced VIC-20, and once we're done with this, when you know the pin out, you'll be able to power several different machines, not at the same time, but just by changing the plug, so it makes it semi-modular. Okay, let's get ready to lash it together. Right, we're back here again, and this time I've been out and I have soldered up some of the components that goes on the back of this interface. We've got a couple of the 9 volt AC connectors. The 5 volt DC has to go through the front panel for serial and parallel, so this is what this loop here is. And I've heat shrunk it, so I don't know if you can see here, but to the unused pins, you can see inside there, I've heat shrunk each one just to give it a little more stability. Also, because I'm going to be fusing the primary side of the transformer, I've also put some large heat shrink here just because it's exposed where it's connected, so nothing funky there. Now also, let's have a look at the transformer. Now this I bought several years ago, 5 years plus ago, and it's just been sitting there in a box, so I thought I'd use this up. This is the 30 VA unit, if we can see that there, and it says it's got 2 primaries at 115 volts, and it gives the colours as blue, grey, purple, brown. So I'm reading the 0 is blue, 115 is grey, and the 0 is purple. So it's the grey and purple to link together, and you can see that I've just soldered that together, heat shrunk it, job's a good one. So the blue and the brown are going to have, yep, you guessed it, 230 volts on. I've paralleled the outputs, and as we can see here, we've got 2 primaries, 1.67 amps each, just like I described earlier on in the video. And we've got orange and black is the primary side, the first wire of each side, so orange and black I've linked together, red and yellow, and again I've heat shrunk down to a small piece of wire ready to hook together. So here we are, let's open that. Now what we're going to do is I'm just going to lash it together first before we test it, and I'll fix it together properly. So I'll put that in there. We'll offer that up, and as we can see we've got plenty of room. So the first thing we're going to do here is connect up the main side. And just like I did in the test for the transformer, we can see here that it's labelled up live, neutral and earth. So we got red is obviously clearly live. So we'll just stick these connectors in. Live, neutral and earth. I'm not going to, tighten the arsehole out of them at the moment, because we're going to end up loosening them off, because I'm actually going to join the AC side to this on the transformer, so that's going to go in there. For the 5 volts, we've only really got a couple of connections, and that is quite simply this black wire here is going to neg, which is our first one here. So I'm just going to undo that and do that up like so. The red side, yep, you guessed it, that's going to our positive. Right, so apart from being interrupted for the doorbell, here we go again, and you can see that I tinned the wires, and this means that our 5 volt side is hooked up. So let's move the chocolate block out of the way, and let's give this a piece of power. There we go. It's off. Yeah, lovely jubbly. And we can see that is reading 5 volts at 0 amps. So let's turn that off. Take a few moments for the power to dissipate because we've got nothing connected to it except the display. And it's still on, look at that. Right. So we can reassemble the display once it goes off. There's a lot of stored energy. I'll get there eventually, bloody hell. Right, and now we know it's the right way up. There we go, it's gone off now. And we've got the bezel in the right way. There's a small clip here that has to be prized out in order to get the board back in, so we can get in there. He says, well, there we go, and it's clipped back in. So that's fully in there now. Power's all good, and now we can hook up the live side of the transformer. So as I said, brown and blue, guess which way that goes round. We're going to go through the primary side with the fuse. So I'm going to chocolate block this. One, because I like chocolate block. No, because it's easy. And I'll put it right after the video. But it's easier to test and make sure everything's right. So we'll go in there with our live side, the transformer, like so, and that's coming out of fuse. Like I said, I'm going to fuse up the primary side. So in order to bring the supply in, we're going to double up in this terminal here, which is our live. So again, I've tinned the wire so it's not going to fragment anywhere, and I'm just going to slip that in with the fork, hopefully, if it will go. There, lovely jubbly. Now on the secondary side, we've got 2 white wires here that go directly to the plug. So I'm going to take these to 2 more pieces on the chocolate block. Like I said, this is a temporary measure. They're going to get soldered together and heat shrunk properly once I verify everything's working and it is how I want it. Just like that. And we're going to go like that. I've colour coded the wires how it's easier to remember for myself, so, and that one goes there. It's got 3 connections through the chocolate block because of the fuse. The blue is going to get connected directly to neutral, just like this. Again,
There's some sort of problem there. What's going on here? Trying to do this with a camera in the way as well isn't the easiest thing. This is the live side, so try not to fuck it up and blow the arsehole out of it. So that's going to sit there like that. That's going to go in there. That is going to go in there. And it's all going to sit in there like so. Once it's working. Now what we're going to do, we thought there's a lot of room to begin with, that there really is not that much room. Especially when we get the lid on and everything's in place. Like I said, the spigot here will go over the top of that. This will go under it and it'll all line up. So let's just have a quick look. That'll all go together. So once it's done, that'll be in there like that. It'll be together, and then the 4 screws will hold everything in and in place there. See, it can't move at all. Well, once it's all screwed down. So if we turn this on, nothing's cooking. We've got 5 volts on there. Look at that. There's no smoke. And we're drawing bugger all power, as we'd expect. So we'll turn that off and wait for that to clear. And in the next part of the video, we're going to look at actually setting this up, testing it, and making sure we've got the right voltages and this reads right, because a lot of people buy these and they don't set them up. So we'll see you soon. Right, so I've lashed up my 128 cable to the power supply and the load tester, and this is going to become clearer in a moment. Here we can see the 128 power supply is already built in, plugged in, sorry, and this is another one of the units that we're going to use to measure the voltage and the current. Now, people buy these, people make power supplies with them, and they don't seem to actually trim them. Now, I don't know if you can see all right on the video, but on the back there and there, there's 2 little trimmer pots. And that is because after they've been on a slow boat from China, they're unlikely to read right. So what we're going to do is we're going to see just how far out they are. I'm not too worried about ampage, but we can adjust it and get it in the ballpark. So the first thing I'm going to do is power up the electronic load. Okay, and then I'm going to bring the power supply online. Straight away we can see we've got a discrepancy. So we've got 5 volts on the power supply, 5.10 on the electronic load, and we're fairly close on the ampage. So let's just see which one of these bad boys is lying. Clearly one is. There we go. So pull out my trusty fluke meter, and I'm going to measure across these extra terminals on the load. I'll just put that out of the way so I can get a good bead on it. There we go. And look at that. So the load it appears not reading correctly. I'd expect that kind of. It says in the instructions that, you know, there is a tolerance of about 5%. So not great, but at least we're in the ballpark. We've got 5.03 and 5.01. Let's start giving it some Ned Ted. We're at just over an amp. Again, it reads quite well. We've got 1.11 amps on the power supply and 1.06 amps on the load. The voltage is 4.95 volts, and we're getting two different readings now. The fluke is coming back and saying 4.90. The load is 4.95, and yep, 5.01 on the power supply. Oh fuck. Let's give it more. So here we go, we're at just about 2 amps. 2.01, the load is, the power supply is saying 2.05. For me, that's acceptable. Now, here we go again. The load is saying 4.75 volts. The meter is saying 4.73. And we're saying 4.98 on the digital display on the power supply, which is quite clearly fucking bollocks. Let's give it more. So we're up to 4 amps now, and the fluke and the load are reading pretty much the same as you'd expect. There's not a lot in it. And look at the power supply, 4.95. It's absolute porcupine Jack and Ori time. So let's give it some more. So here we are up to almost 6 amps. The fluke and the load are almost reading the same. But look at that, holy shit, 4.93 amps. We're nearly a whole volt out now. 4.93 volts rather. We're a little bit out on the amps, but it's really not a lot in it. Not so worried about that. Let's really crank this fucker up now. .5 amps. The fluke and the load are reading within, within tolerance of each other. Look at that fucking display. That's having an absolute bubble. 4.87 volts. It's 1.5 volts out. So we're going to have to do something about that. So let's dial this back. There's no point cooking its tits off for no reason. There we go. And we're going to shut that down. It'll go off quicker this time because the electronic load's connected. Oh! What a fucking eye-opener. So what we're going to do? Well, for a start, we're going to get in there and we're going to trim it. And see if that makes a difference. So let's get to the back of this. I'll just pop out and leave everything else in situ. As we can see here, absolutely lovely. So what we've got to do is get behind here and trim it out. It's going to be a bit of a pig to get to. But there you go. So as we can see on this one, we've got two adjustments. We've got voltage adjustment down here and current up here. Little terminal driver. Let's see what we're going to adjust first. Let's go with the top one, as that's easier to get to. Now I'm going to just get on the back of that, like so, and I'm just going to tweak that down to 0.27 amps. There we go. So now that's reading 0.27 amps. If you can see that. I'm going to crank this bad boy up a bit. And we're still out. So I'm gonna just turn this over so I can actually get to it. Because I can't see the camera in the way. There we go. Now I'm going to adjust the top end. I'll tilt it back so that the camera can see it at the moment. I just don't want to short nothing with 9 amps running through it. So be damn careful what you're doing, because you're going to blow the arsehole out of something. There we go. 9.1. Come on, you fucker. 9.18. And it changes to 1.6. Look at that. 9.117. So that's tracking that nicely. If we go down now, .77, that's almost spot on. Now the reason why you want to track at the high level first is any error you make at the high level diminishes as it gets towards 0. So at 50%, your error is also 50%. Let's go right down. There might be a slight non-linearity with this. 0.03 amps out. Yeah, that's close enough for me, without a doubt. Now voltage wise, we need to sort this out, because that's clearly fucking bollocks. So now we've got to move on to the next part and straighten out the voltage. And in order to do that, you've got to go on this bottom one. Let's get the screwdriver on it first. There. So let's crank that up to 5.14. And it's not very good at adjusting this thing. Well, that's changing from 5.15 to 5.12, so as you can see. So let's now crank this up a bit. And there's a problem here, isn't there? Clearly. Right, at 9.7 amps, that should be 3.75 volts. So what we're going to do is we're just going to get on that. And that's highlighted a problem. Although the amperage is right, the voltage is not. Let's crank that back down. Yeah. I think we've just discovered that's pretty shit. Right, so we're back again. This is the power supply's put back together. The meter is absolute fucking garbage. Nothing works right with it. If you're measuring current at the same time as voltage, the voltage is just clamped. It can't get down low enough. It's meant to be able to be powered from 4 volts upwards, but the reality is it's so close to 5, it just tells me to go fuck myself. So, as we can see, we've put it back together. It all looks pucker, it looks the part. I've plugged in my C64 cable and I powered up the junker. So let's find out how this works. There we go, 5.15 volts, 0 amps, and there we go. So on idle we've got 0.85 amps. We know that's fairly accurate because I actually trimmed it and measured it against the dynamic load, so that's fine. I'm happy with that. It looks superb. It's about the same size as the others. The design works fine, and it actually feels substantial, even though PETG is a bit more flexible. So let's try firing this up with Kung Fu Flash. Here we go. Straight into a game of Mutants. We're at 0.93 amps now. So C64, Kung Fu Flash, 0.93 amps. Look at that. No real issue there at all. The sound's working fine, so we know that the AC side of the power supply is good too. Yeah, I don't know what happened there. So let's fire up this bad boy. This is a Sidekick cartridge, and it's got a Pi 20W in the bottom. So this is really going to draw a bit more power. Takes a few seconds to start up because the Pi's got a boot internally. There we go. I do like these cartridges. So we've now kicked up to 1.10 amps, which is still absolutely bugger all really. Let's have a look what we got here. If we go into browser, yeah, one load, 64 collection V3, superb. A whole load of stuff in there. This is not the latest version. I do suggest you check this cartridge out though, it's really nice. Let's have a look at this. Here we go. So at 1.13 amps, nice and steady. Brilliant SID tune. Lovely jubbly, look at that. So the power supply is doing exactly what it's meant to do. It looks cool having a blue light on it. I'm really pissed off about the fucking stupid voltage situation, but at least the ampage works right. I am going to come back to this. I'm going to cut this video short, and I'm not going to do the 1581 yet because that's got two of these fucking retarded displays in it. I'm actually going to see if I can find a better display with the same footprint, or print a new end panel and then revisit this and just replace the end. So right now we've tried a Kung Fu Flash, a Sidekick 64, and we're pulling 1.12 amps, which is fuck all. Let's try an Easy Flash 3. Ah, 0.96, I pulled more than I thought it would. So let's jump into something here. Look at that. That sounds like a fucking strangulated cat. I bet that's the junker. I've probably got something like a bloody Swinsid or some shit in there. Yeah. Didn't like that idea much, did it? Okay. Now, where's my fucking diagnostic cartridge? Oh, fuck knows. Right, next thing to try. Let's try Ultimate 2 Plus. Yeah. Look at that. 1.04 amps. That's it. That's not pulling much at all. So far we've plugged a Pi into it. We've plugged several different cartridges. One of them Pi based, an FPGA based one, and it's just not even sweating. My poor SID chip sounds a bit rough though. Okay. I don't expect this to pull much, but here we have a tape cart. Look at that. 0.85, so that's bugger all. Superb. Don't know what this is. Some demo or other. Oh yeah. Yeah, lovely. Okay. Don't like that. That's a Vic glitch, that is. Right, so far that all looks pretty good. Yep, I'm calling that a win. I've got some rubber feet to stick on the bottom of the power supply. The same with the 1581 one when I build that. And I think I'll just do a small follow-up video. But those displays are absolute fucking garbage. But making a power supply, as you've seen in this video, is really easy. Anyone can do it. And you can just get off the shelf parts and string them together. Okay, on that note, I'm going to say check out 8-Bit Retro ReFix, and thanks for watching.